I got a feeling well. I was thirsty. I haven't like that was at least. Yeah, that was thirsty. Yeah. You know, I was honest about it. Me and my ex-girlfriend got really. I don't remember. So hopefully that's or you just know that everyone. Probably. Oh, that's like first year. I'm even partying. So. I'm gonna put it on the excuse me for sandwich. When I do it, it's not. It's not actually rough. Oh, but I think it's
100%. I don't know how I got that many marks,
very bad in history.
you're just that good.
I guess I thought that's
Just that good. You got 3 times more than what you.
Yeah.
Exactly.
Like.
Like, actually, it could be that I know she might have to rock.
Much like my answer on the test, it was several orders of magnitude larger than my accuracy. But yes, she looks at
I can't wait that test with small hundreds. I should not. I'm just astonished. I got All right, well, I hope everyone had a good Thanksgiving. What I want to do today is I want to recap what we did last time. It was a week ago, but we were using complex numbers to analyze our AC circuits, so circuits driven by sine waves that involve resistors, capacitors, and inductors, in principle, in any combination. We're specifically looking at the case where the inductor, resistor, and capacitor are in series, and this is the circuit that you started analyzing last week in the time domain, and you're going to look at again tomorrow in the frequency domain. So how does the current behave as we vary the frequency? So let me remind you of the strategy that we adopted. We said we were going to write our input voltage and our current in terms of some amplitudes times a complex exponential. The only difference between those exponentials is that we were going to allow the current to be shifted by some phase relative to the voltage. And our goal was to try to figure out how to do this. What we ended up doing is we wrote down a differential equation that we got from Kirchhoff's loop rule. And the real advantage of the e to the j omega t was that now we're taking derivatives of exponentials, which just gives you the exponential back again. And we realized that as soon as we substituted our derivatives back into the loop rule, the differential equation, we could express the voltage loop rule as in some voltage provided by the function generator was equal to current times something involving inductance, current times resistance, that's the voltage across the resistor, and current times something involving the capacitance. And what we ended up doing is we defined these quantities, j omega L to be the impedance of the inductor, 1 over j omega C to be the impedance of the capacitor, and if we wanted to, we could say the impedance of the resistor is just R. Impedances are going to combine in series and parallel exactly in the same way they do for resistors, so we don't have to do anything new there. And what we ultimately came to realize is that for any circuit that we could write in this form where we have a function generator providing a sine wave, and then some combination of resistors, capacitors, and inductors, we could represent that entire combination as some net impedance. For our series circuit, it's just the sum of the impedance of the capacitor, resistor, and inductor. And in that case, the amplitude of the current that we're going to get will be the amplitude of the input voltage divided by this magnitude of the impedance. And the phase, or the tan of the phase, will be the imaginary part of the impedance divided by the real part of the impedance. And what I want to do right now is I want to show you that we can get the solution that we got last time using just a couple lines of algebra. We're not going to write down differential equations. We're not going to write down e to the j omega t, any of that stuff. We're just only going to work with the impedance. So for the series LRC circuit, what we have is that the impedance was equal to the impedance of the resistor plus the impedance of the inductor plus the impedance of the capacitor. Okay, we could do our trick again where we could multiply this last term by j over j. The j squared becomes a -1. And so we could write this as R plus j omega L minus 1 over omega C. The minus sign coming from the fact that we had the j squared. What we ended up doing is we ended up factoring out an R, and so we decided that we were going to, well, in fact, I'm not going to do that. Let's just leave it like this. So notice that this impedance is just a complex number. It has a real part. So this is X is equal to the real part of the impedance, and it has an imaginary part that we would call Y is the imaginary part of the impedance. And so it's everything in that square brackets. What we know about complex numbers is we could write any complex number that is expressed as X plus JY as a magnitude times e to the j phi. And so that's what I'm going to do. And we're going to just use the fact that we already know the magnitude of z is the square root of x squared plus y squared. But x is just r. So we end up with r squared plus y squared is just the stuff in the brackets here squared. So it's omega L minus 1 over omega C all squared. And that's it. We ended up, now I'll do it. Now I'll factor out the R. So we decided that we'd like to write this as R times the square root of 1 plus, and then it turns out to be omega L over R minus 1 over omega RC squared. So if we go back and look, we said that the amplitude of the current is just the amplitude of the voltage divided by the magnitude of the impedance, and we're done. We've already calculated the magnitude of the impedance, and so we can say, therefore, the current amplitude is given by the voltage amplitude divided by the magnitude of the impedance, which is just V naught over R divided by the square root of 1 plus omega L over R minus 1 over omega RC all squared. And that's it. We didn't write down any differential equations. We didn't mess around with trig functions. We just immediately did a bit of algebra on our impedance and get the amplitude of the current. And the phase is just as straightforward because we said the phase or the tan of the phase was equal to y over x. Y is omega L minus 1 over omega C. X is R, so we just have to divide these two terms by R, and it ends up being just omega L over R minus 1 over omega RC, and that is our solution for the current in an LRC circuit. The current amplitude and phase and an LRC circuit. So what I want to do today is I want to think about what the shapes of these functions look like versus frequency, and then you're going to measure that in the lab tomorrow. Yeah.
You're explaining again why when you factor out the g in the beginning of the equation, it turns into -1 divided by W.
Oh yeah, it's just we started. So you are happy with this expression, right? All I did was multiply by j over j. So that's going to leave me with a j in the numerator, and then the j squared in the denominator is going to give you the minus sign. Yeah. Okay, so before we look at the shapes of these curves, what you'll actually measure is not the current. The oscilloscope is good at measuring voltages as a function of time. So we're going to measure the voltage across the resistor. The voltage across the resistor is I times Z. And if we want just the magnitude or the amplitude of the resistor voltage, that's just equal to the amplitude of the current times this Z. Okay. And so what we're going to do is we're going to say, all right, let's think about the ratio of the amplitude across the resistor divided by the amplitude provided by the function generator. So this is the resistor voltage amplitude, and then this is the signal generator amplitude. Okay. So what are we going to get? We're going to get I naught times Z. Well, we've got I naught written here. So let's see. Sorry, I've confused myself a little. I have a mistake here. That's why I'm confused. If I want the voltage across the resistor, what should I write down? Current times what? Resistor, right? Yeah, that's my mistake. So there we go, fixed it. So then we just want I naught times R divided by V naught. But I naught we've just written down here already. If I divide by V naught, I'm going to cancel the V naught in the numerator. If I multiply by R, I'm going to cancel the 1 over R in this numerator. And what we'll be left with is 1 over the square root of 1 plus omega L over R minus 1 over omega RC squared. Okay, so you will measure this in lab 4, part E. So what I want to do is I want to construct some plots of the phase phi and of this ratio of voltage amplitudes. So let's examine the frequency dependence of this ratio of amplitudes and of the phase. So I'm going to set up some plots here. The first plot will be, whoops, sorry. Is this the page I want? Yes. The first plot will be this ratio of amplitudes, VR divided by V naught. Okay, as a function of frequency. Oh, where is it? Oh, this is the wrong page. Sorry. Here we go. So frequency. Okay, and then below that plot, I'm going to have a second picture. This will be the phase as a function of frequency. The phase is going to go negative. So I'm going to put my horizontal axis in the center there. All right. So the way we're going to approach this is we're going to look at the limiting behavior. So let's look at omega goes to 0 case. Okay. I'm actually going to start with the phase because if we know something about the phase, it will help us actually understand the amplitude. We said the tan of the phase was going to be equal to this. So which of these two terms is large at low frequency? The first term or the second term? The second one, right? We're going to be dividing by a small frequency. So this second term is going to become large. And so at sufficiently low frequency, this will be like minus 1 over omega RC. And if we go to really low frequency, this is minus a large number. How, like, what do I have to put into tan phi to get a minus infinity or a minus a large number? Where does phi go? Really big negative numbers. If I plot tan of phi versus phi, it looks like this. And so when is tan going to minus infinity? It's down here. What's this angle correspond to? Yeah, it's negative what? Yes, exactly. It's minus pi over 2. And just for future reference here, where it goes to plus infinity, that's plus pi over 2. So this is a large negative number, and that means phi is going to go to minus pi over 2. So that's our first bit of information. We can go to our plot here. What's that?
go to zero though, if it's going to a large number. And
No. So let's see. We're going to low frequency, so I'm dividing by a small number, yeah. So this is minus pi by 2. And this is where our graph starts. Okay. So now we have to think about this amplitude ratio. Notice that we have omega L over R minus 1 over omega RC. That's the same thing that's in the square brackets here. And so at low frequency, everything in the brackets is going to go to minus 1 over omega RC. But I'm going to square it, so I don't care about the minus sign anymore. And then I'm going to add 1. But omega RC is already a small number, so 1 over that is a big number. I can also ignore the plus 1. So let's see what happens if we do that. So I'll skip the page here, and so we're still working on the low frequency case. So this is omega goes to 0 case. Then we have the ratio of amplitudes, what was 1 divided by the square root of 1 plus, so it was omega L over R minus 1 over omega RC. That's what we had. And so now we're going to say, well, we're going to ignore the omega L term compared to 1 over omega C. So it's 1 over the square root of 1 plus 1 over omega RC squared. And now we'll say, well, 1 over omega RC is still a large number, so I don't need to worry about the plus 1. And so then we get 1 over omega RC, because the square root is going to kill the square. And then that is just omega RC. So at low frequency, it looks like our voltage ratio has some linear dependence on the frequency. And the slope is this RC. All right, so then that means here at low frequency, we get something that's kind of linear. So this goes as omega RC. Okay, so fair enough. What we're going to do now is the high frequency case. So omega is large case. All right, again, we'll start with the tan of the phase. That's omega L over R minus 1 over omega RC. This time it's the opposite, isn't it? If the frequency is large, 1 over omega RC is small. And so it's only the first term that dominates. And so that's omega L over R. Now it's the same argument we made before. If omega is really a large number, then it goes off to infinity. And tan phi goes to infinity when phi is plus pi over 2. So this corresponds to a phase is equal to plus pi over 2. Okay, so we can go do that. We can add that to our plot. So I can say, let's see, 1, 2, 3, 1, 2, 3. So that's about here is plus pi over 2. And I'll draw sort of a dashed line that extends out to high frequencies. Maybe I can draw a dashed line over here as well. Okay, so and then at high frequency, we think we're going to approach a phase of plus pi by 2. All right, so fair enough. Let's do the ratio of amplitudes. 1 plus omega L over R minus 1 over omega RC squared. Okay, so borrowing what we already know from our analysis of the phase, the bracket's just going to be omega L over R squared. So we end up with 1 plus the square root of 1 plus omega L over R squared. Again, if we're thinking of a high frequency limit, that omega L over R is large compared to the +1. So we'll ignore the +1 and we get something that looks like R over omega L, right? If we ignore the 1, take the square root to kill the square, and then invert the denominator to put it all in the numerator. Okay, so this is proportional to 1 over frequency. So that's different than what we saw before. Let's go add that to our plot here. So we have something that is like 1 over frequency looks something like this. So this is proportional to, what was it? It was omega L in the denominator and then R in the numerator. All right. So we've got those two extremes. What we're going to do next is we're going to try to find a special frequency. So the special frequency we're going to find in the following way. So we're going to define a resonance condition. This time, what I'm going to do is I'm going to start with the ratio of amplitudes. So it was 1, right? We keep writing down the same thing. 1 over 1 plus omega L over R minus 1 over omega RC squared. Okay. The resonance condition is going to be at what frequency is this ratio the biggest it could possibly be? So what would you do? Like I can't do much with the 1 plus, there's nothing I can do with that. What can I do to make this quantity large as it can be? What do I want to do to the stuff in the brackets? Right, it's something squared, so that's always a positive number. So I'm always adding something to 1 that's positive. What's the smallest number I could add? 0, that's right. So the ratio VR over V naught is a maximum when this omega L over R minus 1 over omega RC squared. Well, in fact, I don't have to square it. I'm just going to set it equal to 0. So what I'm going to do is I'm going to say the frequency at which this happens is a special frequency. And I'm going to label that special frequency as omega naught. So the maximum occurs when omega equals omega naught, where omega naught is 2 pi f naught is the resonance frequency.
So the large, so VR over V naught, the largest it can be would be 1.
Yep.
Yeah.
Yep, that's right. That's what we're gonna, yes, we're gonna put that on our plot in just a second.
Okay.
So let's figure out what omega naught is using this condition. So we have omega naught L over R minus 1 over omega naught RC is equal to 0. If we solve for omega naught, what you're going to find is, well, let's see, we can just cancel the R's out. We bring this negative term to the other side, multiply by omega, so we'll get omega naught squared is equal to 1 over LC, take the square root, and omega naught is equal to 1 over the square root of L times C. So if you know L and C, you can find this frequency where you expect a peak in this voltage ratio. Essentially a peak in the current is what we're going to find. So, and then exactly like you said, at omega equals omega naught, the voltage ratio is going to be 1 divided by the square root of 1 plus, well, it's just 0 squared. And so that's just 1. And so that's exactly what you predicted. And so we go to our plot here and we say, all right, somewhere over here is going to be the maximum possible value of our plot, and that's going to sit at 1. And so maybe it's over here. And so we extend this down, we hit our frequency axis, and we say that frequency is omega naught. And there's going to be a point that sits right there. Okay, while we're here, I'm just going to extend this frequency down so that it crosses our horizontal axis for our phase as well. Okay. So for the phase, we said that tan of phi is equal to omega L over R minus 1 over omega RC. But now we're sitting at this special frequency. And so what does this have to be? 0. We just said it has to be 0, right? It's right there. And so if that has to be 0, right, these things are the same. So this is equal to 0. And if we go look at our plot of tan phi, it is 0 when phi is equal to 0. And so that means that phi is equal to 0 when omega equals omega naught. All right. So then what we do is we go back to our plot and we say, okay, I've already marked omega naught on my plot, and there must be a point that sits right here where the phase is equal to 0. And so that's quite useful because if you're in the lab and you're working on the oscilloscope, what you can show on your oscilloscope, you have 2 channels. You can show your function generator on channel 1 and your voltage across your resistor on channel 2. Then you adjust the frequency until their phases align so that they peak at the same time. And that will be one way, a very nice, quick way of finding your resonance. Okay, good. I want to look at one more case, but I'm not going to do all the algebra for you. I'm going to leave it as an exercise for you to do. Yeah.
Does this imply that V naught and VR actually?
At that one special
That
frequency.
one special.
Yeah. Yes. Yeah. Okay. So then what we'll do is we'll say, okay, last case. The last case is the following. I want to set the frequency to be omega naught, our resonance frequency, but plus or minus gamma over 2. Remember, we have this gamma where, so we now know omega naught is 1 over square root of LC. We've been using gamma. You measured it in the lab last week. It should be equal to R over L. Okay, and so we are considering this case when omega naught is much bigger than gamma. So with that, one way to think of that is we make the resistance small. So we have not so much dissipation in our circuit. And that's called the underdamped case, where you get lots of oscillations. They take a long time to decay. So this is the underdamped case. Okay, so here's a challenge for student. So show that when omega is equal to omega naught plus or minus gamma over 2, the voltage ratio is equal to 1 over root 2, and tan of phi is equal to 1, which implies that phi is pi by 4. In fact, what I should do is I should say plus or minus 1, which implies that phi is plus or minus pi by 4. In order to do this, you're going to have to make use of the fact that omega naught is much bigger than gamma. But I think you can do it. So let's go back to our plots here. And let's see what that's going to look like. Over here, like root 2 is 1.41. 1 over root 2 is like something like 0.707, 71% or something like that. So there's a line over here, which is the 1 over root 2. And there are some lines over here. Ooh, I'm gonna adjust a little bit where I was gonna put that. So there's a line here. This is going to correspond to omega naught minus gamma over 2. And then there's like a symmetrically placed line on the other side where this is omega naught plus gamma over 2. Okay, and so what we're going to have is a point here and a point here. And then for our phase, we keep extending these lines down like so. And so somewhere halfway between 0 and pi by 2, we have pi by 4. And then we have minus pi by 4. And what we're going to get is a point that sits here. And a point that sits at plus pi by 4 over here. So what we can do now is we can try to connect all these regions together. And, you know, I probably won't draw it perfectly, but it's going to look something like this. Go. There we are. That's the phase. And then for our resonance ratio of amplitudes, we're going to get a peak right at the resonance frequency. And then we have to go through all these points, and then we have to connect to this 1 over omega. There we go. Not bad. Okay. And so this is what you're expecting to measure tomorrow. One interesting thing that we haven't added on here, if this is minus gamma over 2 away from omega naught, and this is plus gamma over 2 away from omega naught, that means the width of this resonance at the 1 over root 2 height is just gamma. And this width from a phase shift of minus pi by 4 to plus pi by 4, that has a width of gamma in the frequency. So it's kind of interesting. There's these parameters that we used for the transient response. Gamma controlled how quickly the oscillations decayed. It also controls the width of your resonance. Omega naught was the frequency of your oscillations in the transient response. And it's also the resonance frequency in this frequency domain picture. So it's the same set of parameters that are controlling what happens in both the transient time domain response and this frequency domain resonance that we've just seen. Okay, we have quite a bit of time left. What I want to do is see if we can understand physically why is it at low frequency that it's the capacitance that determines this linear shape of our resonance, and why at high frequency do we have inductance involved but no capacitance, and why when we're at resonance do we see no phase shift. Okay, so those are some of the questions that we could ask. All right. So we've done the analysis, we're ready to do the lab. Let's see if we can sharpen our intuition in understanding the behavior of this circuit. So questions could be, why does VR over V naught go as omega RC at low frequency? Why does VR over V naught go as R over omega L at high frequency? And why is phi equal to 0 when omega equals omega naught? Okay, so let's start with those questions and we'll see how far we can get. Okay, so let me draw the circuit. We have L and C and R, something like that. And then we have a current, I, is in our circuit. And so we could say, well, what we like to do now is we like to represent that as our signal generator providing V in, and some total impedance, which for us is going to be the impedance of the resistor plus the impedance of the inductor plus the impedance of the capacitor. Okay, so that's sort of the stuff we know. If I did a loop rule around the circuit on the right, I would say V in minus I times Z is 0. And so that means I is equal to Vn over Z. Okay. The voltage across the resistor is IR. And so that means that's just Vn R over Z. And so if I wanted to look at the ratio of those voltages, that's going to be R over Z. Okay, good. So that's a starting point. So let's see. We have R in the numerator. I'm not going to do anything with that. In the denominator, we have, well, we have a series circuit that includes a resistor, an inductor, and a capacitor. Okay, the impedance of a resistor is just R. The impedance of the inductor is J omega L. And the impedance of the capacitor is 1 over J omega C. All right, good. So this is our starting point for trying to understand some of these questions. Let's start with low frequency. So omega goes to 0 case. Well, we've already thought about this case. We already concluded that in this case, the impedance of the capacitor is large. And we ignored the J omega L. And we ignored the +1, which is equivalent to ignoring this R. So in this case, 1 over J omega C dominates. So what I mean is it's large. The impedance of the capacitor is large at low frequency. Okay. So therefore, this VR over Vn is equal to R divided by 1 over J omega C. I should say, let's say it's approximately true when the frequency is low. And so that means this is J omega RC. And we can see the omega RC that we had before. So it's like our circuit, which we started as inductor, capacitor, resistor. When the impedance gets really large, it's like we can ignore this inductor and we can ignore this resistor, and everything is controlled more or less by the capacitor. Okay. Notice that this is a ratio of the actual voltages that includes both the magnitude and the phase. So let's see if we can understand, how can I interpret this J times an omega RC? So let's return to Euler's equation. Let's look at Euler's equation. Euler's equation said that e to the j phi was equal to cos phi plus j sine of phi. I'll first show you what some people call the most beautiful equation in math. So let's consider phi is equal to pi. Okay, all I'm going to do is wherever I see phi, I'm going to put pi. E to the j pi is equal to cos of pi plus j sine pi. All right, what's sine of pi? 0. And cos of pi, -1. And so there it is. We end up with e to the j pi is equal to -1. And so the reason people like to refer to this as one of the most beautiful equations in math is because it brings together a bunch of really important constants. Like you could hardly overstate the importance of E. And pi is obviously an important number. J is the square root of -1. That's kind of this new thing that we have. And so all of these things together, producing -1 is kind of an astonishing sort of result. These E and pi are both known as transcendental numbers. And so you have this transcendental numbers, including the J leading to this -1 whole, is really surprising. So I like it a lot, but for me, it's Euler's equation that's really has all the beauty. This is just one special case for Euler's equation. Let's do something else. Let's do phi is pi by 2. And let's see what happens. Okay, so e to the j pi by 2 is equal to cos pi by 2 plus j sine pi by 2. Okay, what's cos of pi by 2? What's sine of pi by 2? 1. Okay, so we have a different version of a similar kind of thing. We could say e to the j pi over 2 is equal to 1. Sorry, it's not 1. What's it equal to? J. It's 1 times j, or just j. Well, hold on. That's kind of interesting because if we go back to here, I have a j. So I could write that if I wanted to as e to the j pi by 2. So therefore, we have this VR over Vn is equal to j omega RC at low frequency. And so what we're going to do is, instead of writing j, let's write it like this. So that's the same thing as omega RC times e to the j pi by 2. All right, well, what I'm going to do is I'm going to start to deconstruct this a little bit. What do I know? I know that VR is I times R over Vn equals omega RC e to the j pi by 2. But what do I know about I? I has a phase factor, right? So I could write this as, let's see, I is an amplitude, e to the j omega t, e to the minus j phi, right? I could write this as e to the j omega t minus phi, and then I could separate the difference in the exponential as a product of exponentials. And Vn is some amplitude, e to the j omega t, I could cancel the e to j omega t's if I wanted to. And so sure, why not? Let's just go ahead and do that. I still have a factor of r over here. In fact, why don't I put my r times the I naught? So we'll do I naught times r. And what's left? It's omega rc e to the plus j pi by 2. And so this I naught r over v naught is just the ratio of amplitudes. We're back to ratio of amplitudes that we had. E to the minus j phi is equal to omega rc e to the j pi by 2. And the only way the left and right hand sides could be equal is if the coefficients multiplying the exponentials are equal and the arguments of the exponentials are equal. And so VR over V naught is omega RC. That's already what we have in our drawing. Phi is equal to minus pi by 2. And that's what we already have in our drawing, right? So here, low frequency, phase is minus pi by 2. Low frequency, this goes as omega RC. All right, good. We answered this question. Let's answer the next question. What happens at high frequency? Okay, so the high frequency case, omega goes to infinity. All right, so we will start with the voltage across the resistor divided by the voltage at the input was equal to, let's see, we wrote that down up here. Where did we go? R divided by the impedance. Okay. J omega L plus 1 over J omega C is approximately what? Well, high frequency, 1 over omega small, we ignore that. We'll say frequency is large enough that we can ignore the R2. And so this is R over J omega L. Well, J, we saw that we could write that as e to the j pi by 2. Okay, so that's R omega L e to the j pi by 2. Sorry. E to the j pi by 2. So, well, I could move the exponential up to the numerator if I wanted to. So we get R over omega L. Oh, that's kind of nice. That's what we've seen on our plot of the ratio of amplitudes. E to the minus j pi by 2. And if you go through the same argument that we did before, where we write this as current times resistance, we could cancel factors, and we'll see that this coefficient, R divided by omega L, must be equal to the ratio of amplitudes. And we would end up here with an e to the minus j phi has to be equal to e to the minus j pi by 2. And so phi has to be pi by 2. And so what we get at high frequency, so omega large, is the following. And if we go look at our plot, that's exactly what we drew. High frequency, pi by 2, and R divided by omega. All right. 1 minute. Maybe we can answer the last question in 1 minute. Why is the phase equal to 0 when omega equals omega naught? Okay. So when omega equals omega naught. Well, what did we say? We said that we wanted J omega L minus 1 over omega C to be equal to 0 when the frequency was equal to omega naught. This was our resonance condition. So resonance condition. Okay, so then if we were to write VR over VN is R over the total impedance, which was R plus J omega L minus, let's say plus 1 over J omega C. Well, this stuff is equal to 0 when omega equals omega naught. And so what we're left with is R over R, R1. That makes sense for the ratio of amplitudes. But what about the phase? Well, if I wanted to, I could take this and I could multiply it by e to the j0. Okay, right? E to the j0, j times 0 is just 0, e to the 0 is just 1. So I'm multiplying by 1. But if we did all those manipulations that we did before, we would end up with VR over V naught e to the minus j phi is equal to 1 times e to the j to the 0. And that would lead to the coefficients have to be equal. That's what we saw already. And the phase has to be 0. And that's what we put in our plot. So the takeaway from this is when you have an impedance that is purely real, no imaginary components, your phase is 0. It's when your impedance is non-zero that the phase it's when the imaginary part of your impedance is non-zero, that's when you get non-zero phases. And you'll get positive phase shifts if that imaginary part of the impedance is one sign, and you'll get negative phase shifts if it's the opposite sign. And so that really corresponds to, does your imaginary part of the impedance, is it more inductive or more capacitive? Will determine whether the phase is positive or negative. Yeah. Yeah, if you wanted to go think of everything that we're doing has its foundation in electromagnetism. So you can, in principle, talk about all these things. Let's see. Okay, wow.